All right, where even were we? We were talking about representations. Did we finish representations? Feels like ages ago. So we talked about binary representations. Okay, real value, this is where we ended, right? So real value, this is where, okay, well, we don't have discrete values. We've got situations where, like a lot of times with like evolutionary computation, look, you can think of any problem that's dealing with real numbers, you know, is going to be like a real slash floating point problem, right? But for a lot of what we're doing, because remember how I was talking about like TSP and n-queens, these are toy problems. And these are problems that we, like, they're very important, but we love to study because they're easy to wrap our head around. And so when it comes to the real, like the real number problems, we are wrapping our head around, like, well, we're just picking a lot of times arbitrary functions as our benchmarks. And so I shouldn't say arbitrary. Like there's like a suite of common real number problems that we love to play around with. So here's an example of one called the Ackley function. So like imagine for a moment this is a two-dimensional problem, right? So what we're doing is we're moving along these two dimensions here. Let me scroll up. So I got x1 and x2. I'm moving along these dimensions, so I can like move along like the surface of this area. This dimension here, I know it looks like, no, that's a three-dimensional problem. Not quite. It's two dimensions. We have two dimensions that we can play around with, but the fitness is some function of these two dimensions, okay? So here, this would be an example of like a minimization problem. I want to find the xy coordinate that happens to have the smallest fitness, like it's a minimization, okay? I want to find the one with the smallest value. Here, I believe the minimum point is 0, 0. I believe that's the optimal solution is the point 0, 0. But if you're starting with random floating point numbers, you're not going to land on 0, 0. Hell, you're probably not even going to ever find 0, 0, right? Like you're just going to be, like it's real numbers. They're floating point numbers, right? There's always some crazy decimals associated with these things. So we got to find the minimum here. And you can get a sense from this. I don't know if it might not be clear, but like, do you have like, can you wrap your head around what this looks like? It's just, think of it like an egg carton, right? It's got these like bumps. And it just so happens that in the center is this like crater to the center of the Earth. I don't know. So if we're using an algorithm that likes to follow a gradient, for example, and when I say gradient, just to remind you, what I mean by that is, if I'm standing on the side of a hill and I want to go to the lowest point, it's probably good for me to walk down the hill, not up the hill, right? That's like the gradient, right? Follow the slope. Now, if I'm standing right here, and I'm like, oh, follow the deepest slope, I'm gonna be like, well, that way looks pretty good, and I'll go right down to the center, if I'm following this gradient. But if I'm here, and I follow, I'm gonna end up in this little like trough. And then I'll be like, well, I'm following the slope, but there's gonna be a point where I'm basically at the bottom of the trough, or goddamn close to it, and I'm never gonna, like, I'm never gonna get out of that little trough. I'm like stuck in it. So this is like a deceptive problem. There's a lot of local minimum. We're looking for the global minimum, right? I want to find the smallest value of this whole space, but there's a lot of local minimums that are like relatively good to their local area, but I can get stuck in them if I'm only going to do like this gradient search. Is that clear? So this is a classic problem. There are a number of like fun real number problems. Some will even be like moving, which is always kind of interesting. Like imagine this is the case, but like this is like moving, and so your search has to like dynamically follow and track these things. It's pretty neat. Anyways, this is one example, the Ackley function. If we click this, I'm pretty sure it takes me to a list. Let's see, optimization test functions. There's a lot. Oh, come on. I'm curious if we can, no. Like, look at this one. Ooh, right? There's a lot. This is just some guy's website. Like, this one's actually going to be pretty easy, right? If you follow just this, you can find the optimum by just finding some like slope, like hill climbing algorithm. Something like this, good luck. Cool. There are certain forms of evolutionary computation. So all you need is a representation that works with this. So if you're using a genetic algorithm, okay, instead of starting with random integers, start with random floating point numbers. Yeah, that'll totally work. But there are some forms of evolutionary algorithms that are specifically designed for real number problems because they are kind of like their own, I don't know, like genetic algorithms are great for discrete spaces, but it has some shortcomings. There are some like evolutionary algorithms that are specifically designed with some features and ideas in mind that help it with the real numbers. Basically, there are whole different algorithms that are specifically targeted towards real numbers. Now, if you do and if you go and you look at these algorithms that are specifically designed for these, like, to work with real numbers, you will find, like, if you do that and you look at the algorithm and you say, like, but that really is just a GA. Well, yeah, welcome to evolutionary computation, because evolutionary computation is just an evolutionary algorithm. They're all evolutionary algorithms. They're all remarkably similar. It's just how we change out those modular bits is where we can start to get different, like, classes of these algorithms, even though they are all, at the end of the day, so goddamn similar to one another. All right. And just for the record, just because it's always good to have this recorded, there are 6 people here, not 20. Just saying. Okay, tree representations. So this is where genetic programming comes in. I just talked about different algorithms that are designed for specific things. Well, genetic programming, at the end of the day, genetic programming is really just a GA. It really is just a genetic algorithm with a very specific, even though it doesn't even need to be this, but traditionally speaking, genetic programming is just a GA. And I realize a GA is just an evolutionary algorithm. Yeah, but genetic programming really is just a genetic algorithm with a specific type of representation and genetic operators that go with this representation. But at the end of the day, it really is just a GA. So if and when we get to genetic programming, we will go into more detail on it later in the course. When we get there, and you think, that's just a GA. Yep, it absolutely is. And I was saying, so genetic programming typically uses tree structures. We call them S expressions for symbolic expressions. Has anyone ever heard the phrase S expression before? Well, you are all familiar with them, whether you like it or not. But this right here, this is a tree, this is a tree, this is a tree. And each of these trees, these 3 trees, represent 3 different programs. 3 different programs for 3 different problems. This would not be like 3 members of a population for the same problem. No, no, these are like different trees that would be reasonable for different programs. Does anyone know? Well, this particular program is just a mathematical expression. Like it or not, it's a function, but it's a mathematical expression. Can anyone tell me what this function is, just by looking at it? What would be your guess? 1.2 minus x times y, right? That's like what you were saying. And so we could draw this. If I draw this over here, can you see that back there? Would you be able to see? If I'm drawing this, what I would draw is you always start with the root. And you would say, okay, well, we're multiplying. And what are we multiplying? we're multiplying 1.2 minus x, right? But really, we're multiplying like minus. I'm going to just redraw it as a tree, and then I'll kind of show you how we build it. And then over here we have y. And in these trees, you'll notice we have operators and operands. Operators are applied to some value, and operands are some terminal of some kind. In this particular one on the left, it's going to be a variable or a literal. So over here, we've got the terminal 1.2. It's just the literal value 1.2. And over here, we have some variable x, and this is some variable y. So this is the tree, but what is it? Well, it's the multiplication of 1.2 minus x times y. No, that's the idea. Okie dokie. So if we were to look at this one, this would be OR of if checking the length is less than 5.2 and it's not red. So this would be some classification. So this is some problem working on, like this is some function of numbers. This right here is clearly some function of like multiple different types here, because here we have like a length, which is clearly some number. This is apparently floating point number. And some red, that's like a Boolean, I guess, if not red, like true, false for some red value, right? So we have different types here. And here we've got a couple, like this is a little bit more advanced, right? We've got like an if. If open and right closed, go forward, otherwise turn right. So this would be like some program, some instruction for how a robot can navigate a space or something, right? So if straight ahead is open and my right is closed, take a step forward. Otherwise, turn right. I don't know. I don't know if this will be good or anything. It's just some tree encoding some program for how a robot can navigate some space. Do you see how these represent like functions, programs, mathematical expressions? They're all the same thing. But do you see how they can represent there? Yeah. So genetic programming, typically, conventionally, let's say, it wants to evolve programs to solve problems. So where a genetic algorithm is going to be used to solve like TSP, come up with the best permutation for a Hamiltonian cycle that minimizes the distance, right? Genetic programming says, I've got a problem, like I want a robot to navigate a maze. So I want to use it like an evolutionary algorithm to evolve the program to tell the robot how to navigate the maze. Like that's the idea there. We usually represent them as trees, like this. So we don't have like a list of cities. We have a tree representing some program. And, okay. And we need special genetic operators to work on a representation like this. Because like if you were to say, do a one-point crossover, you're like, well, what does that mean? Right? We're going to talk more about genetic operators for trees a little later. But do you get the idea? Different representation. And there's necessarily, we would need like new genetic operators to work with a representation like this. So the above figures show 3 different tree encodings that would be useful for different problems. The leftmost represents x point, yeah, there we go. This could be useful for a regression problem. The center tree represents a Boolean expression. Length is less than 5.2 or not red. Maybe it's a classifier. The right is a conditional program. This could be programming a robot to traverse a maze. The tree is made up of operators and operands. Operators are the interior nodes and the operands are the leaves, right? Hopefully that was like clear. I mean, it would necessarily be true. Some operators are binary. They need like 2 operands. Some are unary, need 1. And in some cases, you might even have one that has like 3. But it has like some special rules. Because like this is a condition, do something else. So the operators are rather broad, and the operands are rather broad. It's just really, it comes down to something that is a function of multiple inputs and something that is a function of, well, none, because it just is what it is. Cool? Questions, thoughts, concerns, points, observations? Anything? Happy, sad? Okie dokie. All right, yeah. Okay, cool. What is this? Yeah, okay, that's just the link. N Queen's genetic algorithm. I think I say... Okay, no, I don't. Perfect. So let's go back to N Queens. Let's say we're implementing N Queens. At this stage, I realize we have all... Presumably, you did assignment 1, at least enough that you got a GA working for TSP. Good. So now let's talk about how we could implement a GA for N Queens. I just want to check something here. N Queens. We're probably going to skip this topic. So let's, maybe. We'll see how it goes. So we've already used a GA. We've been familiar with the GA. You used a GA for TSP. Well, now let's use a GA to solve a different problem. And we'll see, hopefully by the end of this topic, you're going to get a clear picture of how, okay, you knew the idea of a GA, and now, and you picked all the pieces, like your representation, your fitness, how you're going to evaluate, how you're going to select, what are the operators. You've picked all these things for TSP. So now we're going to do the same thing, except we're going to see how we can switch out a couple of the things to make it work for a different problem. A similar but different problem. Because we already talked, like, our representation is still probably going to be a permutation representation. And there are some genetic operators that work really well for permutation problems. So some of it's going to be very similar, but there are going to have to be some significant changes, like fitness is going to be wildly different. How we translate an encoding to the phenotype is going to be quite different. But we just get a chance to see the differences there. Any questions about where we're heading right now? So hopefully this is going to be clear. Okay, so, and going back, we used a GA to do the bit string, right? So clearly we saw a different version too, but that was a pretty cheesy problem. So the optimization version of N Queens is going to be used. So if you remember, the optimization problem is not the constraint problem. The constraint problem was, is it valid or not? We're going to make it the optimization version because it works a little bit better for the GA because it provides a gradient. If I have two, like, if you're using is it valid or invalid, if I have two configurations, one with 2 conflicting queens and one with 7, which one should the GA pick? Probably the one with fewer, right? Probably. Maybe I'm wrong, but probably. So we want to have a way to rank solutions, and an easy way to give a rank to the solutions is to make it the optimization version of the problem. So instead of it's valid, invalid, it's going to be how many conflicting queens are there? How many queens can attack one another? And if one encoding has fewer than the other, that's good. Any concerns or thoughts about that? I'm really wanting to make sure we're all on the same page before I continue. All right. All right, so given an n by n chessboard, place n queens on the chessboard while minimizing the number of conflicting attacking queens. In other words, minimize the number of queens in the same row, columns, or diagonals. That's what we want. So here is a valid configuration of a n by n, or a 10 by 10 chessboard that is valid, right? This is actually, this particular style of solution is called like the staircase style. And you can see none are in the same row. So there's going to be one queen in each row. One in each column. And none of the diagonals are going to have more than one queen in it. Right? And same with this way. Cool? Cool. All All right, the reason the optimization, okay, I already went on about this. Yeah. Okay, and we also talked about previously, what kind of encoding are we going to use? We're going to use the permutation encoding. If you weren't here for that, we could use an encoding where we use the 2D list of lists. So, and then it's like a binary encoding where each cell is a 0 or a 1, whether there's a queen there or not. But that's a huge search space. And so we work to reduce it by closing that gap. And we work to reduce it by coming up with a permutation problem where, perfect. We turn into a permutation problem where where we have a list of n values, n numbers between 0 and n minus 1, or 1 to n, however you care to do it, where each value in each index of that list corresponds to a column, and the value in that index corresponds to a row. So because there's only one value associated with each index, we know we can only have one value, like one queen in each column. And because we know the values in each cell are unique from one another, it's not possible to have queens in the same row. So we're in great shape. So the permutation representation previously discussed will be used. A chromosome will be a list of length n. Each of the n indices corresponds to each of the n queens. Each index will be the queen's respective column. And the elements within the list will be a permutation of integers between 0 and n minus 1. The value at each index will be the queen's respective row in the chessboard. Any questions about that? And I'm asking this, I'm hitting this hard because it's clear, it must be clear what we're doing here before I carry on. Yeah, we're happy, okay. Since the value of indices are unique, no two queens can be in the same row or column. An example chromosome where n is 8 is 057863214. If I were to draw this, I'm not going to. Should I? I think we're all pretty clear, right? Yeah. Yeah. All right, cool. So a population. So, okay, the representation is going to be a list of integers between 0 and n minus 1. Great. We can generate that with Python's random library. Great. A population. That's going to be a list of lists, okay? So the chromosomes, and thus the population, will be randomly generated for the implementation of a genetic algorithm, okay? So this is how we're going to create it. I realize I'm always, like, at this stage, Raise your hand if you're in the diploma program. No one's in one person? You are? Are you in the diploma program? Yeah? Did you take a Python class before? Python.
Some classes.
You've had some classes with Python? How about you? With Python. That's really what I mean. And so like you're familiar-ish with Python. Yeah. So the reason I'm asking that is because there's a lot of Pythonisms in here, and I assume some familiarity with Python. And I wonder if in the future I should go and change this to make it a little bit more general coding-y. But let me just explain. I create a population. It's just going to be an empty list. Population fitness, empty list. There's going to be one value for each member of the population. So if the population has n things in it, I'm going to have let's say m, right? We have a population of size m. I'm going to have a population fitness with m things in it, where each index corresponds to each, they go together, respective. So for whatever in range of the population size, some value I predefined, create a chromosome. So this is sample, that's from the Python math library. I say, from the numbers, this is range. Who here should remember what this creates? If this was Python 2, you'd be absolutely correct. In Python 3, it's slightly more nuanced than that. It just creates an iterable thing, which is not quite the same, but effectively it's a list. So this will give you a number between 0 and n queens minus 1. And then I say pick from this sample n queens, but it's like pick without replacement. So basically, this is an easy way to generate a permutation. There are other easy ways to generate a permutation with Python's math library. Random library, but that's one way to do it. And then I'd go to the population and append to it. Cool? Cool. 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 So the number of chromosomes in the population, we would define some hyperparameter called population size. The length of the chromosomes will match the number of queens, which is defined by the hyperparameter n queens. And the chromosomes and permutations of the chromosomes are permutations of the sequence of integers from 0 to n minus 1. Note that sample is from Python's random library. It returns a k-length list of unique elements chosen from a population sequence. By the way, these don't need to be the same. For our problem, they do. But in general, for Python sample, they don't have to be, right? Okay, yeah? Questions, thoughts, concerns? Please, you gotta stop me. Are you being quiet because you're like, yeah, no shit, get on with it? Is that what's happening? Say, do you want me to get, yeah? Let's just have a look here. Sample. So, it's got a couple of things in there, but if we just go look at the docs, return a k-length list of unique elements chosen from the population sequence. Don't confuse population with population. Used for random sampling without replacement. So basically, I give it a set of values, and I say randomly pick k of them without replacement. So if I give you the values like, for example, 1, 2, 2, 5, 3, 7, -1. These are, I pulled these out of my ass. They don't matter in any way. They do not need to be unique. They just need to be I shouldn't have called them set, a multi-set of values. Then I say, if I said pick k, if I said k is like 4, I say pick 4 of these things. 2, 5, 1, 2. So I take from it without replacement, meaning once I take it, I can't pick it again. Now, why are there 2 2s? Well, because there were 2 2s here. It's not possible for me to get a third 2. As k can never be more than the length of this, though, because as I take more and more things, there's no more, I can't pick any more. In our case, what we did is I said, make that multi-set, it's just going to be a set of 0 through n minus 1, and then pick all of them, and it's just going to be an easy way to generate a permutation. Clear? Yeah. Yeah.
Does sample always choose the numbers in a random order, or does it go like one after another?
Sample, it better be a random order. Random sampling without replacement. So it better be random. So random, right? I don't want to hear anyone in here go like, there's no such thing as random inside. I know. We all know. Thanks, asshole. We know. But yeah, that wasn't directed at you. That was directed at any future person who wants to be like, they're pseudo-random. Yeah, we know. Take it easy. Whoop. Other questions? Returns a new list containing elements from the population while leaving the original population unchanged. The resulting list is a selection order such that all subslices will also be valid random. Yeah. This allows raffle winners, the sample, to be partitioned into grand prize. I don't know what that means. Members of the population need not be hashable. Well, that's nice. If the population contains repeats, then each occurrence is possible selected, like we said. Some examples. Yeah, there we go. Cool. Other questions about this idea? All that matters is this was a way to generate a permutation. There are a lot of ways to generate permutations. I'm sure you could use like a shuffle. What method did you use on assignment 1 for generating your permutations? What did you do? You used shuffle. That would have worked here too. Anybody else use something different? You muscled it. Nice. All right, cool. I'm with you. I'm really bad at using the standard library. But at the end of the day, that's doing the same, like it's doing, what you did is what this stuff is doing. What did you say you were doing?
Random.
Just random, yeah, cool, yeah. All right, now evaluation. I'm gonna warn you, this is not going to be immediately clear, but I think it's rather simple. But you're not gonna understand it by first look. It's not critical that you understand this fully, to be clear. It's fine if you're like, what? Okay, I'll just take it for granted. That's fine, because it's not really about a genetic algorithm. I'm just showing you how this fitness works. Okay. First, let's read the docstring. Oof. Okay. Count the number of attacking queens in the provided queen's placement. To count each attacking pair only once, the check for attacking only happens in the forward direction from index 0 towards n. With the permutation representation, attacking can only happen in a diagonal. Thus, the check for attacking is to check only plus minus offset, where offset is the number of indices away the queens are from each other. For example, consider the chromosome whatever, whatever, 4, 3, 6, 1, whatever, whatever. The question marks mean they're not important for this example. These are the values that are important. The queen at index 2 is attacking 3 queens. So how do I know that? Well, it attacks the queen at index 3 as it is offset 1, and 4 minus 1 equals 3. So its offset is 1, and 4 minus the offset is 3. It is attacking the queen at index 4, 2, 3, 4, 6, as it is offset 2, and 4 plus 2 equals 6. Is that clear? And it is attacking the queen at index 5 as its offset is 3. 4 minus 3 is 1. So notice that it actually goes in both directions. We need to check like 4 minus 3 and 4 plus 3. We need to check both directions because it's like, is it up their diagonal or their diagonal? Basically, the plus and minus tell us if it's plus, well, I guess it depends on which way we're counting. Is 0 in the bottom left or in the top left, right? If it's in the top left, the minus direction is checking this way. If it's here, the minus direction will be checking this way. And then the positive would be checking that way, and then this would be that way, depending on where our origin is. Does it really matter where our origin is? No, as long as we're mentally consistent with where it is, we're happy. Here's a question for you. Do any of you do any significant amount of drawing on your computer? No?
I do a little bit for like my animation class.
You do? What do you use?
Fire Alpaca.
Is that like, so like, how do you fit?
Oh, you mean
Like, you're psychotic. And I say that because that's what I do, and I think it's psychotic. I have like a little bamboo board, but I can't get, you know, those little boards with a pen, stylus, but I can't quite, yeah. I can't really get it. Anyways. All right, so that's the doc string. So let's see if we can figure this out. I know you're like, okay, this is a lot. Okay, total attackers. So this is not calculating the fitness for a whole population. This is for a single chromosome, okay? A single chromosome's fitness. So what do we do? Well, start with a running total called total attackers for attacker column and attacker row in enumerate chromosome. So remember a chromosome, this will get me, remember enumerate? Raise your hand if you know what enumerate does. Uh-oh. One person. Okay. 2 people. All right. All it does is, it's like a for loop that says for each thing in a collection of things, but it also tells you the index of that thing. So if I have a list that's like a happy face, a letter Y, a angry face, and what else? I'm out of ideas. Come on, help me out here. An X? Come on. a tree. There, that's my tree, right? If I were enumerating over this list, I would get the pair 0, happy face, 1, Y, 2, angry face, and 3, tree. Haha, nice. That's the idea. So that's what enumerating is doing. Now, here, it's convenient because the values in here represent rows. And its corresponding index represents columns. So we get attacker column, attacker row. Isn't that nice? It's beautiful, really. I think that's quite nice. See? You're like, yeah, it is. Right? Cool. Then for victim index, in range, attacker column +1, because we're going to start, range, remember, start and index. So start, well, we don't need to start on our current index. We're only ever going to start on our next to me. And we're also only going to check our attacking in one direction. Let me make sure, I mentioned that earlier. Let's make sure it's clear. I want to count, perfect. If I'm looking at this queen here, and I want to count the attacking queens, I'm only going to ever check for like queens I can attack in this diagonal and this diagonal. I'm never going to look backwards. Never. And the reason I'm never going to look backwards is I only want to count this one once. So this is I'm counting pairs of attacking queens. So this is one pair that can attack each other. I don't want to count this one can attack this one and this one can attack this one. No. So not count those, I'm only going to ever look that way. So when I'm looking at this queen, and I want to start looking for queens that I could attack going that way. I don't want to start at my current index. I want to start at my current index +1. All right? So victim index, start at my attacker column +1, and go to the length of the chromosome. That's the number of queens. That's a stand-in for that. In fact, maybe this should be n queens, but whatever. The length of the chromosome, because it goes up to but excludes that value, right? So basically, starting next to me, go to the end. Clear? Unclear? Happy? Sad? Okay, offset is going to be the victim index minus the attacker column. That's the offset. So how many steps away am I? So the first time through this loop, the offset will be 1. The next time through the loop, the offset will be 2. The next time through the loop, 3. And then the next, 4, and so on and so on and so on and so on. Victim row will be, well, the chromosome at that victim index. Right? So which row is the queen in that column I'm currently looking at? Note that victim index and victim column are the same thing. That's what that means. The blank look on your face, I don't know if you're happy or sad, or you're bored because this is so obvious. Make it more obvious. Animate your face. Smile. See?
How does it check? How does it know to not look behind itself?
Because the inside, so the outside loop is which queen am I worried about? Who is it attacking? The inside loop is look at all possible queens it could be attacking. And so that inside loop, if we go, come on. If we are here, so the attacking queen is in column 0, 1, 2. The way I know never to look backwards is I only start looking at my column +1 to the end. And that's where this part is here. Start at my column +1 and go to the end. That's what that inside for loop is doing. Does that answer? You're happy? Yeah? Cool. Good question. So, okay. I know my offset. That's just the difference of my column and the column or the index of the queen that I could be attacking. and I know which row it's in, because I could just look it up effectively. Well, I'm looking at that victim index, which victim index at the chromosome, well, that tells me the row. That's the row. The value in the chromosome is the row that queen exists in. Yes? Yes, yes. So if attacker row minus offset is equal to victim row, or attacker row plus offset is equal to victim row, they're attacking. Add 1 to the total. If not, do literally nothing and go to the next loop. Like look at the next queen. Or next queen, next column. Until we finish looking at all the possible columns, go to the next queen, look at all the columns. So for here, we start here. By the way, 0, 6, does that correspond to? No, it doesn't. If I'm here, obviously this is not a full board because we're missing queens here and here, but it doesn't matter for the sake of checking. I'm here. I will look at this column. Its difference is 1, and we're looking at 6 and 2. Is 6 minus 2 equal to, no, 6 minus 1 equal to 2? No. Or 3, pardon me. Is 6 minus 1 equal to 3? No. Is 6 plus 1 equal to 3? No, so they're not attacking. Look at this one. Is 6 minus 2 equal to 4? Yes, they're attacking. Here is 6 minus 3 equal to 0? No. Plus 3? No. In fact, we're off the board, so it doesn't even matter anymore. Happy? Yeah? Cool. And that's it. I, for one, think this is a nice, elegant fitness function. I think it's nice. It works really well with this representation. This wouldn't work well for another representation. We'd have to really hack this to make it work. So we'd need a different fitness function if we used a different representation. But for our representation, this works quite nice. It is obviously computationally expensive. Right? You know, we can say loosely it's going to be like n squared, right? I mean, we know it's like half of that, but you know, it's n squared. Why? Well, I'm just going to cheese it and be like, well, there's n queens. I need to check n, you know, n squared. It's not that bad, but it's that bad. So it's not too bad. You think TSP, right? Well, TSP, assuming we had like a lookup table where we like pre-generated the distances, it's like linear time, right? You just sum up all of the distances for each member of each value in the chromosome. Well, this is n squared, but also keep in mind that n for TSP is going to probably be a lot bigger than n for n queens, right? Because of the whole nature of the problem. This whole explanation is just going into what I already described. So how do we calculate the fitness for the whole population? Just put it in a loop and do it for each member of the population. That's it. I'm going to store, okay, index, so this chromosome, so the first chromosome's fitness is going to be put into the beginning of the population fitness. The next one's going to go right after it. The next one's going to go right after it. Cool? Cool. Selection, I'm just doing tournament selection. That's it. We've seen this before. Randomly select some indices using choices here. Chromosome tournament selection. Mating pool -1. Now, directions -1 because it's a minimization problem. Who here used tournament selection for, by the way, on assignment 1, did you use, like, I gave you like the selection and crossovers that you could use. Did you use the ones I gave you? You used it? Cool. Like, good. Like, you didn't have to, but if you didn't, you worked too hard. Now, when I said go invent your own, okay, go invent your own, but yeah. Mind the direction argument. Yeah. Tournament selection. We looked at this already, right? Yeah. So it's just tournament selection. Variation operators. Well, we can't do 1-point crossover, so we could do something called like order crossover. We will, like, I won't go into detail on this, but which crossover did you use for assignment 1? Do you remember?
I use order crossover.
Order, how about you? Which one did you use? Order, how about you? Do you remember?
No,
Yeah.
Yeah, I use this.
and I make my own.
You made your own? Did I not, also, did I include partially mapped? I didn't, oh man, I thought I had that one in the, all right, never mind. Let me check real quick. Yeah, that's not gonna work. Is that it? Really? I thought I had more. All right, whatever. There's another popular one called partially mapped that works pretty well too. Anyways, we'll end here for now. I'll see y'all
Wednesday.
tomorrow. That's tomorrow. Yeah, cool. All right, see you.